Hello and welcome to our Feedback Control Systems project on the Telesurgery robot. I'm Bailey Burrows here with Chao Pan and Alex Sofreya.
Telesurgery robot will allow accuracy to assure surgery is performed correctly with low error. Control engineering can apply a control to the plant to meet the desired specifications. We decided to analyze angular position of the instrument and voltage associated with it.
Our group decided to model the system as a DC motor hooked up to a spring and damper in parallel. The spring and damper were chosen because cables would stretch and flex like a spring, while the gripping mechanism would cause friction, hindering movement slightly like a damper. The system input is voltage, while the system output is angular position, rotating the current operating tool to the angle specified by the surgeon.
This is the block diagram used for our system. Below it is the circuit diagram for the mechanical system N of S seen above. These are the closed loop and open loop transfer functions derived from the block diagram on the previous slide. When we plotted the closed loop transfer function with resistance and impedance values of 0.5 and all other values at 25, the step response plot seen on screen was obtained.
The roof Hurwitz test was applied on the closed loop transfer function with the previously specified values, which resulted in a Bible-stable transfer function, and which you can see the first column is all positive. When the final value theorem was applied, steady state error goes to infinity, which indicated that we needed a controller.
Disturbance was analyzed to determine how the system is expected to behave when disturbed. When the closed-loop transfer function's disturbance was analyzed, we conclude that a step response disturbance would result in the system being affected because the limit of the function is 1, while a ramp response disturbance would not affect the system because the limit of the function is infinity.
A proportional derivative controller was added to the system because of the system's spring and damper in parallel. From the PD block diagram, the closed-loop transfer function seen was derived. This addition brought the steady-state error to 1.
When the PD transfer function is plotted in MATLAB with rise time of half a second and percent overshoot of 5%, the plots seen on screen are created. The yellow region on root locus plot indicates where values do not meet the specified criteria. With dominant poles moved to the acceptable region, the desired rise time and percent overshoot are displayed in the step response plot.
Here you can see the Simulink block diagram of the system with a PD controller. With the closed loop, specifications, and CISO tool, we found a KP value of 1 and a KD value of 0.265.
From the previous Simulink block diagram, the step response on screen was obtained. This plot shows that the system meets the desired specifications. When the Nyquist plot of the closed-loop transfer function was plotted in CISO tool, it shows the system to be bibostable.
For robustness analysis, the Bode plot was created for a system with PD controller, which shows a decrease in gain with the use of controller and an increase in phase margin.